Okay, so it's my pleasure to welcome you here, and I'm sorry for the late date after the end of the term. It's mainly my fault and my family's fault because of the late arrival. And this was supposed to be a talk a month before my departure, but it turns to be a talk roughly a month after my arrival. And the good news here is that if you find there some ideas or things that we might discuss or collaborate on, I'll be still staying here with CRCS until late August, so we have 3 months to go and discuss things that you might see beneficial to you or ideas that you would suggest back to me. I'm visiting CRCS, as I said, and I'm from Czech Republic, from Masaryk University. And what I want to present here is a couple of things that I've been working on recently, mainly with my PhD students and colleagues, and that is basically a couple of projects that concern wireless sensor networks with intrusion detection and deployment of mechanisms for privacy protection. And this is the brief outline of the talk. I'll give the necessary wrap-up of wireless sensor networks and the constraints that they give us. I will have a brief sidekick project presentation on credibility of simulations when we use them for wireless sensor networks, as researchers very often do use them instead of real test beds. Of course, I will introduce the basic issues of privacy in sensor networks, and then the main focus of my presentation will be the conflicts between privacy mechanisms and intrusion detection in wireless sensor networks. I will give you one example of one protocol that we have been playing with recently, and I will try to go a little bit on the thin ice to delve into the principles for cooperation between IDSs and privacy mechanisms in sensor networks. And should the time allow, I will have then a brief bonus presentation on some issues related to key management in sensor networks at the end. So what are the sensor networks? The concept that we have been hearing for well over a decade already. Basically, they consist of two types of nodes. One is plentiful, the sensor nodes that have some kind of environmental sensor for humidity, temperature, light, and you name it. And of course, they are not only sensing, but they are communicating the information, so they have a radio. And we want them independent of the outside environment and of any infrastructure, so they are typically battery powered. Either just battery powered, or we have been seeing first really useful prototypes of not only battery powered, but solar, typically solar power enhanced as well. The challenge is that these kinds of nodes and the communication in between them, they bring us to existing research in distributed systems, is that they are of very low computation and memory resources, and also they have very with respect to the battery, they have very demanding position in terms of communication. The papers that first appeared in the area of sensor networks 10 or 15 years back spoke of networks with hundreds of thousands nodes and so on and so forth. I have to admit that I have never heard of a real test bed that would deploy more than hundreds of nodes. The other difference to what has been envisioned 10 or 15 years back was at that time it was expected there would be one or very, very few of so-called base stations. The second type of, or the second component of these sensor networks that we assume has substantial computational and memory capabilities, let's assume laptop-like capabilities, and we consider them having unlimited or nearly unlimited energy resources, at least with respect to the other sensor nodes. It has been shown recently with the first real deployments of the sensor networks that actually as we go low with the number of nodes to tens or hundreds, we typically go higher with the number of base stations, so we don't have like one center hub, but where you will see the sensor networks deployed would be monitoring environment. So we have, for example, valleys and hidden areas where the normal communication through satellite or mobile network doesn't go through, but node-to-node communication goes through. But you'll have so many other nodes that would be, or positions that would be within the reach of satellite or mobile network, that these base stations you will see typically deployed in low percents of the nodes within the sensor network. In any case, we have to assume multi-hop communication between the nodes. Then we can differentiate between sensor networks that are purely static or have mobile nodes. In terms of scale, there can be some substantial differences. And what is very interesting to us in security research and cryptography research in wireless sensor networks is whether the sensor network is in a predefined topology. That means we can take care of some key management before the deployment of the network, or whether the nodes are just spread and we have to assume that we don't know the neighbors or how the neighbors will actually happen to be, and the network has to self-organize itself after its conception. Application-wise, the first networks came with military applications and perimeter protection. We see more and more of them actually with wildlife monitoring, these smart environments, and especially healthcare applications. But the latter, we will again find these with, again, back to the numbers, tens or hundreds of nodes within the network. And some of them would be mobile, but for most of the environments, we would have some nodes within the network in a fixed position and only some mobility. The nodes in the sensor network or the overall network processes very often sensitive information, and we want to protect that information. As I mentioned, we are constrained with respect to energy and computational power. And we have to consider that we want to avoid costly calculations. And typically, as you would know, cryptographic calculations can be pretty costly. And even more costly transmissions. The nodes, one of the benefits of the nodes is that they are deployed somewhere where they don't have to be physically protected. We save on manpower and deploy the nodes. And typically, we will see that the nodes should be cheap. The cheaper, the better. Which, on the other hand, brings us into problems. You will see hardware in the sensor node that has very limited, if any, temper resistance. Which is unfortunate considering the different in terms of applications and so on. But in terms of computational power, very similar environment, and these are smart cards. With smart cards, you will see not perfect, but reasonably good temper resistance, with research going on in this area for nearly 3 decades. But you will see very often, very little of the ideas from the smart card world being deployed in the hardware sensors. And I personally see it as a pity. I'm not a hardware researcher, but I see that this being a drawback, and I don't have any real feeling for why the experience from the smart card world is not used within the sensor world. And we have to consider, of course, attackers against either the communication or transmission of the information. We find it useful to differentiate between active attackers that disturb network operation and passive attackers that try to read or deduce sensitive information. With respect to the active attacker, you will see very often the deployment of the intrusion detection systems, things working on fairly similar principles to standard networks. These things are, to much extent, or the basic ideas are deployed in wireless sensor networks. And against the passive attacker that monitors the communication, we deploy some kinds of privacy mechanisms. Before I go on with privacy, one thing that you will see as important later through the talk When you read papers in the area of wireless sensor networks, and more so security in wireless sensor networks, you will see the verifications or comparisons of results being done not in actual test beds, but on simulators. There are numerous good reasons for that, at least the two of them that I mentioned here on this slide. We get fast evaluation of the setting of the security system through the simulator, and we get comparable results without unpredictable environment impacts, so we can compare options, and we can do that pretty fast. One of the other projects that I've been playing with through the last 2 years is basically a project with the vision to provide a framework or broader system that will, as an input, take given sensor network, its environment, types of nodes, and so on, and as an output and type of attack that the network should withstand, and as an output would provide proposed IDS setting, including its parameterization for the given sensor network. And for that, for evaluation of the candidate solutions, we need either testbed or simulation. Of course, we use simulation because we can run it in parallel on a few thousand cores and get the comparison much faster than would the testbed deployment provide. And as an effort that I thought of being summer work for one of my summer job for one of my PhD students to compare simulations and calibrate simulators. This actually went into a project that took 1.5 years and work of 3 people. We have seen, taking 5 of the most commonly used simulators, the results to be drastically different. What we use this simulator for is the detection of the intrusion detection system, as I mentioned, with given evaluation metrics. The simulator simulates always the setting of the intrusion detection system, and through evolutionary algorithms, we tried to devise better candidate solutions for the exact setting, and we compare the benefits of the and drawbacks of different settings. Just to give you an idea what we have been doing, but this is content of other paper that I won't focus on today, and that's a simple network with about 250 nodes, 5 attackers that are dropping 50% of the received packets, and intrusion detection system, and we have been evaluating options of the intrusion detection system being run as an instance on each of the node in the network, on only selected nodes, and how they should be positioned, and so on and so forth. But I won't be going into details of this because this is really not the core topic. This is example of intrusion detection system research. But what I want to leave here as a note is that the simulators, when you, as their user, very often think that you give it the correct and basic setting. When you give this setting to different simulators, you will see that the results between various simulators differ substantially. And that will be for a few good reasons, different buffering sizes, different radio sensitivity being programmed within the simulator, different curves for error rates and signal to inference and noise ratio, and so on and so forth. And as I said, we spent much more time than we actually originally wanted on comparing the simulators. Then we actually went for the Mixim simulator that's based on the OMNET++ framework. But while it's the best candidate out of those that we evaluated, it's not actually the ideal candidate after all. And we evaluated 5 simulators based basically on a broad survey of literature, and we took 5 simulators that are most commonly used in the research on wireless sensor networks. So back to the main topic of the presentation, that is privacy. There can be various types of sensitive information that can leak by the means of wireless sensor network. What is going on? What is the network observing? Where is this thing being observed? When was it observed? Who is carrying a node, or who is being observed by a node? With respect to the direct information leakage, of course, we can use encryption techniques and we can protect the basic information transmission through encryption. However, we have been familiar for quite a few years with a lot of side channels, quite a few decades actually this thing is being played with. And for side channels, we can limit them by various techniques that go against traffic analysis. This is another view on different aspects of privacy in wireless sensor networks. That is basically giving you an idea what different things people might be speaking of when mentioning privacy in wireless sensor networks. And I would leave it at that. I believe that it's always important and useful to look into particular application or family of applications. What exactly is the aspect of privacy that you want to achieve there, and look into that particular goal or protocol. At a very general level, we can see that the principle basically of intrusion detection systems in any kind of network is that it takes inputs typically from logs, tries to link observations from the logs, and tries to infer that there is some kind of activity, possibly unwanted activity going on in the network. Privacy mechanisms do basically the opposite. They try to limit the linkage between different pieces of data. And this underlying conflict actually seems to appear in most of the solutions that we have seen, and the solutions that we focused on were solutions where first either the intrusion detection mechanism was considered, and then the guys came, okay, we need also this and this privacy aspect to be taken care of, or vice versa. And the questions that we wanted to answer in our work, and this is what I'm working on at the moment, is what kind of problems we can find when both techniques are deployed together, and how can we deploy them together so that we don't run into so many conflicts. And before we start, I will say here that as the detection system, we mean one instance of a system running on a particular sensor node. It can run on all nodes in the network. It can run only on selected nodes in the network. And as a privacy mechanism, typically a set, unless I say otherwise, typically a set of protocols that go against traffic analysis. And as an example, let's take a very simplistic privacy scheme where the packets are re-encrypted hop by hop. Identities in the packets will always be replaced by pseudonyms. And the pseudonyms are generated with session key that is derived from a master key. So we assume that X and Y share a pairwise key KM, and always for every new packet, the X and Y derive new session key KS from KM and create a new pseudonym based on the packet sequence number and the session key. While they do that, we have node A that carries the instance of the intrusion detection system, and that can observe the communication between X and Y. However, because of the changes in the identity and changes of the pseudonym, the IDS, if it does not have the access to the keying material of X and Y, cannot deduce that this was a packet that X is addressing Y because of the changes in the pseudonym. What is even worse, if we take not just one packet transfer, but continuous communication, the intrusion detection system cannot determine at all whether X is sending way too many packets and attempts to jam the network. The intrusion detection system is not able to decide whether some packets should be forwarded by Y and where not, and so on and so forth. It doesn't know whether it should monitor the the node Y or not, or whether it should focus on more intensive monitoring of X. And we can run in other issues. Of course, we can say the intrusion detection system or its instances will share the keying material with X and Y. If we do that, and we have the key KM pre-shared with the IDS actually becomes a very sweet spot for an attacker because it has got keys for the communication between the nodes. An attacker that will not get access to X and Y but can get the grab of A or B can suddenly link past and future pseudonyms of X and Y, can even forge the pseudonyms and insert malicious traffic in the network. Okay, this simplistic solution probably won't work, so we can work with pre-shared secrets and partial disclosure. We will say that some session keys will be shared with the IDS. The IDS, one instance of the IDS will not understand all the pseudonyms. However, we have then to make a very elaborate setting of the key management that different IDSs will get different keys, and we have to make sure, or we have to provide with sufficient probability for the ability to monitor each link with at least one IDS to observe the communication in the network against attacks. Another solution might be based on delayed information disclosure, where we would not reveal the KS key to the IDS when the communication happens, but with a delay. The attacker would not be able to forge the pseudonyms, would be able to do it retrospectively, to link them retrospectively. However, the disadvantages that we come to here, the IDS has to log a lot of data, and the attack detection will be coming with a delay. In some situations we might mind, in some situations we might not. The setting that we found useful in few scenarios was combination of the pre-sharing and delay disclosure, where we have the session key revealed only when actively requested by the IDS. The IDS has to pay a certain price for that. The price can be, and this is very useful setting in sensor networks, is in terms of energy, so it has to do some computations or communications, and is paying, it has to balance how many requests it can do. But there are other options for limiting the number of requests. There can be other problems than just this problem that associates with the issue of multiple or hidden identities. Another problem is, I mentioned the selective forwarding and jamming. Another problem is for those who are familiar with the Sybil attacks. The Sybil attacks are attacks basically based on changing identities and disproportionately using capabilities in the network with different assumed identities. But in this scenario, we actually assume for the privacy reason that the nodes have different identities. And monitoring attack of this kind is hardly feasible. What is even worse, even if we assume that the IDS can actually say this is an attacker node, it will be in unbelievable trouble to communicate this to the rest of the network, to tell them who is the suspicious node, who is the attacker in the network, because there won't be any common identifier and the IDs will be changing. We can try to identify it, and some attempts have been done of the nodes using context information like hashes of previous communication and so on and so forth. Another different family of issues we can provide for privacy using randomized sending rate. I will give an example of this scheme in a few minutes, and keep changing the routes. However, we will have big trouble to differentiate between dummy and normal traffic in the network. When we introduce random routing, we will make life much harder for quite a few of the intrusion detection systems because they will not have steady data flow for analysis. The schemes of this type, because of the randomized sending rate, change the forwarding time. This is something that the IDS basically is trying to fight against, because it doesn't want to see delays in the communication that is caused by nodes that forward the information slower than they should be. we can introduce, and as a supplementary mechanism we often do, encryption and changes of packet appearance. However, we won't be, which is obvious, able to analyze packet content, but we will have a hard problem to detect packet modification in terms of dropping packets or injecting new packets. If we provide for semantic security, which is that two messages that are fairly similar to an outside observer will not be viewed as the same or fairly similar, then for the IDS to observe that the packet has been actually forwarded as it should have been and was not dropped, or some other packet has not been injected instead, this will be very complicated to observe for the intrusion detection system. And when we view the complications from completely different angle, the IDS, when it works properly, and we are concerned in the first bullet point with the local attacker, will actually decrease the anonymity set, the set of all suspects of a given action. If the IDS says these nodes should not be considered in the communication anymore, it reduces actually the anonymity set for the other participants in the communication. And on top of that, the IDS traffic itself and observation that the traffic is going on between the intrusion detection systems may leak information, and we might in turn need a privacy mechanism just to protect the IDS traffic on its own. Let's take as a case study a mechanism suggested by Matyáš and others in 2007, which is called periodic collection. It provides for event source unobservability against global eavesdropper. Nodes in this scenario are sent at constant rate, 1 packet per time interval. And when there is no packet in the queue, a dummy one is created. And the packets are encrypted hop by hop. So the scheme would run in such a way, when imagine this kind of network. And if we don't have this scheme, the global attacker would be able to observe that a communication is going on, and gradually these nodes are broadcasting. So it can clearly see that from the bottom to the upper node, the communication went this way, and this is the route of the communication. If we deploy this privacy mechanism, the global attacker will just observe all nodes broadcasting at the same time. Very simple, on the other hand, quite effective privacy scheme. However, the IDS will, in respect to many things, be in a similar position to an attacker. It wouldn't be able to detect packet dropping because it doesn't have access to all. It would have to share the keys with all the nodes in the network. And now it sees that everybody is broadcasting, but it can't read, except for the sender identifier. In this scheme, it can't read whether the packets being broadcasted are the actual packet or dummy packet. Same with respect to modification and injection. However, on the other hand, there are some benefits. The IDS can detect nodes that are malfunctioning or completely dead, and the IDS can detect jamming. Okay? This was inside in one particular scheme for privacy. And a protocol that we have been playing with addressed the issue of detecting packet modification and packet drop, these two particular attacks. And we assume that every node runs a very simple, as you will see, intrusion detection system. We assume communication-wise that the node is able to monitor its children and parent in the route of the communication. And we rely here on the broadcast nature of the wireless medium. We can use few underlying basic security schemes. We chose this one of Masaryk and others. This particular scheme provides for confidentiality with semantic security, provides for integrity, authenticity, and weak freshness. We can order the actions sequentially. And as I said, every node is basically behaving like a very simple detection system. We assume cryptography-wise that always two neighboring nodes share two pairs of keys, KXY and KXY prime, and a counter. And this is the packet with the information that is sent between X and Y. And we can observe here that always for one part of the packet is the encrypted information, M is the message being transmitted, and this is the integrity and authenticity protection provided with the use of MACs and the nonce. Always the nonce is created using the second key, different distinct key from the key used for encryption, and the nonce used in the previous round. What is the useful thing here is that X, when transmitting the information, can calculate the nonce that is used for authenticity protection, for being able to watch whether the node really has been transferred farther or not. It can calculate the NY in advance, and with respect to the modification, node Z, when it receives the message from Y, will only be able to compute the MAC once it decrypts the data sent by the node Y. And this way we can achieve transitive watching on the route between the nodes. To give you some lessons that we learned in examining few mechanisms of this kind, we basically see few things that show same trend as in standard networks. The IDS nodes should not be distinguishable from other nodes so that the attacker cannot selectively attack these IDS nodes. Here we speak of wireless sensor networks, unprotected environment where the nodes are being deployed, and it makes it rather easier for an attacker if they know which particular nodes to pick. Very often the attacker model works with respect to assumption of certain percentage of the nodes that can be picked. But if it's random picking, whether it's random picking or picking of nodes that really carry the intrusion detection system, this can play a very important role to the success of the attacker. As we have seen on the example, attacker can have fairly similar knowledge as the intrusion detection system itself. Attacker, with respect to local attacker, is observing the communication that the attacker node can observe. And we should make sure that the IDS itself will not gather too much information because, again, the IDS is sitting on a node where the node can be physically removed and analyzed by the attacker. What we find as a very useful mechanism is limiting of secret information, limiting of the keying, and key management issues are fairly interesting here, where we limit either in time or space, and we try to achieve limited impact of the node compromise. Of course, as with many other schemes, it's beneficial to us if the behavior of the network with respect to the attacker that we consider stays same and the attacker would not be aware that she is monitored. We found very interesting interplays between considerations of local and global attacker. Very often we might have information that is available to a global attacker and not available to a local one, and similar thing plays often with the countermeasures. We might have countermeasures that work against a stronger attacker, against the global attacker, and might not be so much helpful to a weaker attacker. A very good example is to consider, for example, transmission power. If we set the transmission power between the nodes at the minimum so that it just reaches the next hop and local eavesdroppers cannot overhear too much communication, benefits are that we save on energy, we mitigate the local eavesdropper. However, we help a global eavesdropper because from the global perspective it's much easier to observe where the communications goes from and to. And we make life harder definitely for the intrusion detection system because only very few instances of the intrusion detection system will hear more than 1 or 2 broadcasts when the information is transferred. When we set the transmission power to maximum, we make life harder for the global eavesdropper However, to a local eavesdropper who can observe certain part of the network with the maximum transmission, we make his life much easier. And we make life much harder for ourselves because we will have to deal with interference issues within the network, and that can be sometimes quite complicated. So the things that we basically are still playing with is consideration whether the ideas and privacy mechanisms are really contradictory. As we said, the ultimate aim of ideas is to detect an attack or attacker. The aim of privacy mechanism is to prevent information leakage. And while we have seen majority of the mechanisms for privacy and ideas in conflict, we have seen non-interfering good privacy mechanisms that work together with the intrusion detection system, or as I have shown in the example of the protocol, thing that achieves basically both together. We have focused so far on the items 1 and 2 in the second half of this slide on the on-demand disclosure of trapdoor information and use of probing and testing of suspicious nodes by the IDS, where we actually, when I take the mechanisms from the privacy area, the dummy packets, these don't have to be so dummy after all. These can be packets created by the intrusion detection system and can be actually testing and probing the network. And things that we want to look on still would be threshold schemes for the trapdoor information availability and involvement of trusted third parties, although with respect to the last item, I'm fairly skeptical because, excuse me, because of the cost in terms of communication, and communication with trusted third party typically is rather demanding. What we have seen when working in this area for through the past, that there are some protocols that try to address some privacy goals, but very often assume weak attacker model, and we found them for real applications very often impractical in terms, namely of efficiency or high latency. This is typically for mechanisms that come from traditional networks and make many assumptions that don't hold true for wireless sensor networks. We are basically aiming at the goal, one with our work, and that is to propose privacy mechanisms that would offer multiple modes of operation, dynamically changing network that would provide different levels of privacy protection throughout its lifetime by detecting the attackers. And we have found it to be rather tricky, though ultimately rather useful, to have metrics that would allow us to measure different levels of privacy in wireless sensor networks, but this is basically a problem of not only wireless sensor networks, but in general most of the information and communication systems, to be able to measure the level of privacy and compare different mechanisms with respect to their effectiveness. So I try to convince you here today that privacy protection is important property for sensor networks, and to give you an idea that they might, the information might leak both directly or through side channels, and that we have techniques that limit such leakages, but as I have tried to show you, they have some problem or another, and they could definitely improve. These are further readings. Those indexed ones are works of others that we have been building on. Unindexed ones are pieces of our work through the end of last year, and some submissions for this year, and even some accepted publications from last year. And I hope that I do have a few minutes. So if you don't have questions directly to this, which I will be willing to definitely address even later on, I don't care, I will give you an insight in a slightly different area that we have been playing with, and that concerns key management that we use for the privacy schemes. Let's assume that we have a sensor network where some of the paths between selected nodes are compromised by an attacker. The so-called is somebody familiar with the amplification protocols? The amplification protocols if I make a very simplistic example, if the node A and B know that the KAB is already known to the attacker, they try to establish a new key using the route through the node C. Okay? And these schemes sometimes work and enable you to establish and resecure the communication, as you see with the first three examples here. But sometimes you might, of course, be out of luck and you transfer the key through a link that was compromised and you don't achieve the success. It's not a perfect mechanism, of course. There have been a handful of protocols oriented towards the node, both with respect to push and pull model. And we have been playing with a couple of my older PhD students, now graduates, for over 5 years now, with the idea of involving evolutionary computing into the game and to try to devise the protocols semi-automatically. We have been successful. We have basically achieved or went for the generation of protocols that achieved all that was already published, and we found better protocols with respect to the security goals. However, the problem there was that they were considerably message expensive, and that was very demanding for the wireless sensor networks. Then we looked onto group-oriented protocols where we don't work with just a single node, or the basic unit is not just a single node. We achieve cheaper with terms of communication designs, but the designs that are fairly complicated for the protocol designer. Again, we work here with a network simulator, with the combinations according to the given setting of the evolutionary algorithm, of the combinations of the parents to calculate or to suggest candidate solutions that we evaluate as protocols in the simulator, and we measure the success in with respect to the quality. The quality is measured with respect to percentage of secured links. And to give you an idea what these protocols can do, consider this, where on the x-axis you have the fraction of initially secure links between the nodes in the network, and on the y-axis you have the fraction of links secured after the secure amplification protocol. So if you have no amplification at all, you go with this blue dotted line, basically, and whatever you had at the start, you still have in the network. However, when we deploy the secrecy amplification, we can substantially improve. And for example, if we start at this setting where we have 40% of the links secure, after the secrecy amplification, we can get to over 80% links being secured in the sensor networks. And this is quite pessimistic consideration. This is only with 40% of the links being secure. When we go ahead with quite, I would say, still very realistic assumption of 60% of the links in the sensor network being secured, we get to something like 97% links being secured after the most successful secrecy amplification that we achieved. And that's the end for real. So thanks a lot for your attention, and I will be welcoming and trying to answer the questions, of course.
I have one question for you, and this is not really my field, so a lot of this is over my head, but I'm curious, when you're, how do you detect the compromised link between two sensors? How do they determine, hey, this link has been compromised, we need to establish it?
That's actually why we use the simulators. And we basically have the setting for the attacker, setting for the benign nodes, and we basically simulate the thing.
Okay, but are you basing it on one of your earlier slides? The example was you're looking at packet loss, and that is indicative of an active attack or something. Is that
Yep, so we make an assumption of this kind that, for example, was somewhere here, that we have, oops, sorry, This is too slow. Where I was. The example with the 250 nodes, 5 attackers in the middle, and with the simulator, we actually simulate how the attackers would be successful in doing what they do with respect to the communication that is going on. So technically, we try to run the simulation multiple times, typically provide we try to go for hundreds of simulations at the same time, and then basically are roughly averaging on that. We don't do just simulations, we do always the benchmarking to the test bed that we have, but as you can guess, it takes time. So while we benchmark something that would concern tens of runs of something in the network, we can run tens of thousands on the simulator.
You have a testbed network that you have a testbed network that you use when you're doing non-simulated runs, or
Yep. At the moment, we have about 200, maybe 220 nodes, but we change the settings depending what my students actually need. So sometimes we go for indoor, sometimes for outdoor, sometimes the thing runs for weeks, sometimes it runs for a day. Yeah. Okay, thank you.